We are now ready to go through and complete the Map Reading Geography Handout. This is the handout that you print off of our course website. So you should have this hard copy in front of you as we will be going through each question, and you will be filling in the blanks as we do. The other things that you will need on hand are the two maps that you downloaded from the U.S. Geological Survey map store, which is the SoCal, California map and the Mount Whitney, California map. Okay, so let's actually start with the first question, which is, what are the titles of the two maps? So the Mount Whitney map, both maps will have the title located in the upper right-hand corner as well as the lower right-hand corner. So Mount Whitney, California is the title of the map. Sometimes it's also called the Mount Whitney quadrangle. So either of those would suffice as the title of the map. When we look at the SoCal map, again, we want to go to the upper right-hand corner where we see the title listed as SoCal quadrangle. Moving down to the lower right-hand corner, simply says SoCal, California. So either of those would be sufficient as the name of the map. The next question asks about projection. So the map projections, we've gone through what is a map projection, and we know that there are hundreds of types of projections. The information on the projection for each U.S. Geological Survey map is going to be located in the lower left-hand corner. And you have to read through the fine print before you actually see the word projection listed. And on the SoCal map, we see that it is listed as a polyconic projection. So that would be the answer for the projection type for the SoCal quad. When we take a look at the Mount Whitney quadrangle, again, we're going to find the projection information in that lower left-hand corner of the map. And here, the projection type, it does say the word projection. And when you read through some of that sentence, you eventually get to the type of projection, which is known as Lambert conformal conic. So notice that the Mount Whitney and the SoCal quadrangles do not actually have the same projection type. And that probably has something to do with the dates of publication. The Mount Whitney quadrangle is more recently produced, and so probably the map makers decided to use a more updated type of projection than they did with the older SoCal quadrangle. The next question deals with map scale. So scale, as you recall, really tells us what is the relationship between distances that we measure on the map and the real distances on the Earth's surface that they represent. So we have two of the three types of scales that we've learned about. Two of them are going to be used on our USGS maps. The first type of scale, says scale right down here on the lower center of the map, is what we call the fractional scale. And in this case, that fractional scale is a 1 to 24,000. But for right now, we're asking you what are the types of scale. So the first type is the fractional scale. And the second type are these calibrated bars. One is in units of miles, one is in units of feet, and one is in units of kilometers or meters. Those calibrated bars, of course, are referred to as graphic scales. So on the Mount Whitney quad, we have both the fractional scale and the graphic scale. When we look at the SoCal map, we're going to see same thing. We have a ratio, which is our fractional scale. It is also a 1 to 24,000. And we have three calibrated bars, which represent our graphic scale. Now, the next question asks, what is the relationship between the real Earth and distances shown on the map? And for this, we want you to use that fractional scale. So we could look at the SoCal quadrangle where we see a fractional scale of 1 to 24,000, which tells us that every one unit that we measure on the map is going to equate to 24,000 of those same units on the Earth's surface. So we could, if you have a hard copy of the map in front of you, you could take your ruler out and you could measure 1 inch along your map, anywhere on the map, and you would know that the real Earth distance that that represents is 24,000 inches. You would probably want to convert those inches into at least feet or perhaps even miles to make a little bit more sense. But whatever unit of measurement we use on the map, one of those is going to equal 24,000 of the same units on the Earth's surface. If we were to measure in centimeters, say we make a measurement with a ruler here of centimeters, 1 centimeter on the map, again, the ratio is unitless. So if we start with centimeters, our scale tells us that we stick with centimeters. In other words, 1 centimeter on the map is equal to 24,000 centimeters on the Earth's surface. So looking at the Mount Whitney quad, because the scale, the fractional scale is the same rule applies. 1 inch measured on the Mount Whitney map equals 24,000 inches on the Earth's surface on this area of the Earth. 1 centimeter on the map equals 24,000 centimeters. If we were to measure an entire foot on the map, that would equal 24,000 feet on the Earth's surface. The next question asks us to use a ruler to determine how many inches there are to 1 mile on each of these quadrangles. So if you have a hard copy of the map, you can take a ruler out and actually use the calibrated bar down here. So you would actually measure, notice here's miles. So 0 to 1 mile, you could either go to the right from the 0 or to the left from the 0, because each of those represent 1 mile for this map. With our digital maps, I have already introduced you to the measuring tool, and that we find under Edit, Analysis, and we're going to use Measuring Tool. So if I use the measuring tool down here on the graphic scale, starting at the 0 and going out to 1 mile, that gives me a distance of 2.64 inches. So notice down on the lower right, there's a little box that popped up with distance tool, and it says 2.64 inches. Now let's take a look at the SoCal map and do the same thing. We're going to come up to the edit box, come down to analysis, select the measuring tool, and looking at the graphic scale, we're going to start at 0 and we can go, this time let's go to the left and let's go out to 1 mile. Whoops. And we want to get it as exact as we can. And it looks like it's very, very close. So it's 2.62 inches is what I'm getting on this map. Again, we can get out of the measuring tool by just selecting that. The next question deals with the types of north that are shown on each of the maps. As we learned, there are indeed 3 types of north. So I want you to practice using the zooming in tool. And as you zoom in on the lower portion of the map, we're going to see the norths that are represented here. So you will recall that all of these maps are going to be oriented with north going straight up on the sides of the maps. So that straight up line there in the middle with the star on it, that represents the North Star or Polaris, which is, of course, our North Pole is oriented with the North Star. So that one right there represents true north. We also know from a previous lecture that any compass used on the surface of the Earth does not actually point to the North Pole or the true north. It points to the Earth's magnetic north, which is going to have a different amount of offset depending on where the map is located. So in this portion of California, a compass is going to point 14 degrees to the east of true north. So we call this MN, the magnetic north. And then the third type of north that we've talked about is called grid north, GN, and that has to do with using these little grid tick marks on the edges of the map to actually grid the whole map if you chose to do that, if you needed to do that for a particular purpose. So on both the Mount Whitney map and if we take a look at the SoCal map, and let's zoom in on this map too, you will see those three types of north are there as well. Notice that the magnetic north is a different amount. It's 17 degrees listed on this map, where it was 14 on the Mount Whitney quad, because depending on where you are using your compass, every location is going to have a different amount of magnetic declination or offset from true north. The grid north is also a little bit different than it was on the Mount Whitney quadrangle. Now, if for some reason your map got damaged and you didn't have a north arrow, you didn't have any of the norths listed on the map, is there any other way that you could determine the direction of north? And if you can get the direction of north, then you can always get the direction of south and east and west. So we have also on the edges of our maps, on the corners of our maps, the coordinates of each corner, meaning the latitude and longitude of each corner of the map. So if we didn't have a north arrow, but we looked at the latitude of the top of the map and the latitude of the bottom of the map, notice here at the southwest corner of the SoCal quadrangle, we have a latitude value of 36 degrees, 52 minutes, and 30 seconds. At the northwest corner of the map, we have a latitude of 37 degrees, 00 minutes. So 37 degrees is a higher value than 36 degrees, 52 minutes, and 30 seconds. Now, if the latitude values are increasing in this direction up towards the top of the map, we know that they're heading towards the maximum value of latitude, which is 90 degrees at the North Pole. In other words, that tells us that this line is pointing in a northward direction. If we think about east and west, let's look at the northeast corner of the map and let's focus on longitude. So the longitude of the northeast corner of the map is 121 degrees, 52 minutes, and 30 seconds. When we look at the northwest corner of the map, the value of longitude is increasing to 122 degrees. So longitude is increasing in this direction to our left, or decreasing in this direction to our right, which tells us if we keep going in this direction, we'll eventually hit the 0 degree longitude line, which is in Greenwich, England, which is to our east. So that tells us that this way is east, this way is west. Moving up to the top is north, and down to the bottom is south. So if you ever lose that north arrow on a map, if for any reason it's not produced, you can actually look at the geographic coordinates of latitude and longitude for the different corners of the map and determine your direction. Now, looking more closely at the geographic coordinates of the corners of the map, notice that there are no directions, north, south, east, or west, listed next to these latitudes and longitudes. Simply put, in the northwest corner of the SoCal quadrangle, It says 37 degrees, 00 minutes, 122 degrees, 00 minutes. So since the USGS does not print north or west or south or east next to any of those latitude and longitude values, the question is, how can you tell which number is longitude and which is latitude? Say you knew nothing about this location of California. Well, first clue is that one of the values is above 90 degrees. You'll recall that the maximum value of latitude is 90 degrees north at the North Pole or 90 degrees south at the South Pole. So we do know that the higher value, the one that is above 90 degrees, the 122 degree value, has to be longitude because latitude only goes up to 90 degrees. So that's one of the clues. The other thing is, why doesn't the USGS put north or west next to its latitude and longitudes? And the simple reason is that the USGS produces maps of the United States. It doesn't produce maps of other parts of the world. So we know that all of the United States is within the Northern Hemisphere. It is north of the equator. And it's also within the Western Hemisphere to the west of Greenwich, England. So because these maps are of United States lands, it should be assumed that we're in the northern and western hemispheres, and therefore the map maker does not need to put N's and W's next to all of the latitude and longitude values. I did work for the USGS for a certain amount of time, and I know that the federal government really watches all of its budget very closely, and my personal hypothesis on this is that by not printing N's and W's on all of their maps, someone in some accounting office figured out that they could save a lot of money in ink and printing if they did not put N's and W's on the maps. Whether that's true or not, I don't know, but it's just my personal idea. Okay, so let's go to the next question, which is actually giving the coordinates, filling out your handout of the coordinates of each corner of each map. So beginning in the northwest corner of the SoCal quadrangle, the latitude, therefore, is 37 degrees, 00 minutes north. The longitude is 122 degrees, 00 minutes west. I would like you on your handout to put the N's and the W's in. The next corner we want to go to is the northeast corner. So we're actually going over to the right corner of the page, the top right, and we see a latitude, again, of 37 degrees, 00 minutes, because we're on this same parallel line of latitude. So that is the same. The longitude has gone down in value because we're heading east towards the prime meridian of Greenwich. So we're now at 121 degrees, 52 minutes, and 30 seconds. As we move to the southeast corner of the map, the latitude has indeed changed because we have now gone down southward towards the equator, so the values of latitude are decreasing. The latitude here is 36 degrees, 52 minutes, and 30 seconds north. We're still in the northern hemisphere, even though we've gone to the south corner of the map. The longitude, however, because we have traveled due south, that has not changed. We're still at 121 degrees, 52 minutes, and 30 seconds west in the Western Hemisphere still, even though we're in the southeast corner. We have not changed hemispheres. So on all of our coordinates, we're always going to have N's for our north latitudes and W's for our western longitude values. The final corner of the map, which is the southwest corner, has a latitude of 36 degrees, 52 minutes, and 30 seconds north, and a longitude of 121 degrees 00 minutes west. Now let's look at the Mount Whitney quad. Now, we're going to also begin in the northwest corner. I do want to say that there is a kind of etiquette for giving geographic coordinates. And that etiquette is that we always report latitude first and longitude second. So by giving that value first, latitude and longitude, we don't actually need to say the words latitude and longitude because it is assumed that the first coordinate given is latitude and the second coordinate is longitude. So always latitude first and then longitude. It's kind of like the sandwiches that a lot of American children like to eat, peanut butter and jelly sandwiches. People just always say peanut butter and jelly. For some reason, people don't say jelly and peanut butter. And that is the way it is with geographic coordinates. We always say latitude first and then longitude. Okay, so looking in the northwest corner of the Mount Whitney quadrangle, we're going to give latitude first. And by now you should easily see which one of these is latitude. It's the smaller number because, of course, latitude only goes up to 90 degrees. And therefore, any value above that, it has to be longitude. So our northwest corner is 36 degrees, 37 minutes, 30 seconds north. Longitude is 118 degrees, 22 minutes, 30 seconds west. Looking at the northeast corner, so as we move over to the right, you can fill this in on your handout yourself. So latitude and longitude. Moving to the southeast corner, again we have latitude and longitude. And finally, completing the loop, southwest corner, latitude and longitude. So the next question deals with distance. How much area, how much distance on the Earth's surface do these maps actually cover? Now remember that degrees and minutes of latitude and longitude are actually distances. They're measurements of distance on the Earth's surface. So at the top of each map, it actually tells you how many minutes and seconds are covered distance-wise on the map. So this Mount Whitney quadrangle is called a 7.5 minute series or a 7.5 minute series map, meaning that the distance in both latitude and longitude between each corner is a distance of 7.5 minutes. Now notice that our longitude value here in the northeast corner of the Mount Whitney quadrangle is 118 degrees, 15 minutes. If we were to add 7.5 minutes to this value, which is the distance between the northeast and the northwest corner, notice that we're now at a value of 118.22 minutes and 30 seconds of longitude. So the difference between those values of 15 minutes and 22 minutes, 30 seconds is 7 minutes and 30 seconds. And that's exactly the amount of distance that the map maker is telling us that this map covers. 7.5 minutes is the same thing as 7 minutes and 30 seconds. If we look at our latitude values, we could start in the southeast corner. We have a value of 36 degrees, 30 minutes. We know that this map is going to cover a distance of 7.5 minutes. So if we were to add 7.5 minutes of latitude to this number here, it should be 36 degrees, 37 minutes, and 30 seconds. Let's see if that's what we get. Yes, indeed it is. So this north-south distance is 15 minutes, is 7.5 minutes of latitude. And the east-west distance of longitude is also covering a 7.5 minute distance of longitude. Now we're ready to look at the questions dealing with the other USGS quadrangle maps that border each of our maps. So the first thing we might want to look at is the very bottom of each map, and let's zoom in on that a little bit. But since these maps are both from California, we actually can see the state outline of our state of California here at the bottom. And that black square there shows the location of this particular map. And we can see where the SoCal quadrangle is located within the state of California. Now, if we wanted to look at an area maybe to the north of this quadrangle, maybe we're interested in checking out some details about the landscape to the north border of our map. How will we know what map we need to get, what other U.S. Geological Survey quadrangle we need to purchase or download in order to look at these areas to the north? So the USGS has two unique ways of giving the map reader, that's us, that information, what other maps we would need to go in any direction off of our current map. Now, this SoCal quadrangle, again, was produced in the 1960s. So this is the sort of older method that was used to indicate bordering maps for our quadrangles. Now, on your map handout, it says, what are the names of the USGS quads bordering each map? And we want you to begin with the SoCal quadrangle, and we want you to begin in the northwest corner. So northwest corner, of course, is the upper left. And notice diagonally, which is the direction of northwest, off of this map, in parentheses, and I'm going to zoom in a little bit more, we can see the word Felton. So the name of that quadrangle to the northwest is called Felton. It also has a code in there. We're not going to worry about the code. We just want to know the name of the map because that's how we would actually look up the map on the USGS store website. If we wanted to look for the map to the north of the SoCal quad, again, we're going to look for those parentheses, and we see in those parentheses the name Laurel. Laurel, L-A-U-R-E-L. That is the name of the map that borders our map to the north. If we wanted to look in the northeast corner, we see Loma Prieta. That is the name of the map, again, in the northeast, to the northeast of our map. How about to the east? So to the east, again, we see the parentheses, we see the name, it's the Watsonville West quadrangle, okay? Even though it's to the east, the name of that map to our east happens to be called Watsonville West. If we look to the southeast, the name is Moss Landing. And if we look to the south and look to the south, we don't see any name there. So what could be going on? Why is there no map to the south? Well, let's think about this. U.S. Geological Survey, I'm going to zoom out here so we can see what feature is on the map in this area. And it's all ocean. It's the Monterey Bay, Pacific Ocean. So USGS surveys and produces maps of land areas. So there is no land in this direction off the map, bordering our map. It's all ocean out here. So that's why we don't have a name of a map, because there is no USGS topo map produced to the south. The same is true for the southwest side, because again, it's ocean, so there is no map name there. And then finally, when we look at the western boundary of the quadrangle, we do indeed see the name of a map. And that map is called, oops, where is it? There it is. It's called Santa Cruz. Here, I'll zoom in again so we can see it in parentheses there, Santa Cruz. Okay, so we should have all of those filled in. But now when we take a look at the Mount Whitney quadrangle, Mount Whitney is a much newer map. published in 1994. So a different technique was developed between the production of the the SoCal Quad and the Mount Whitney Quad. And what we have the same is we see the outline of the state of California, which shows us the quadrangle location. So the Mount Whitney map quad is located in this portion of California where we see that black square, okay? But we don't see any names of maps in parentheses off of the different sides of the map. The new technique uses this little series of numbered boxes where our map is at the center and the boxes numbered 1 through 8 represent all of the different directions, and they're numbered, and then there's a numbered list of map names to the right. So if you wanted to know the name of the map to the south of the Mount Whitney quadrangle, well, we know here's our Mount Whitney quad in the middle, and due south is number 7. So we would look for that on our list, and it says Johnson Peak. That would be the name of the map. If we wanted to know the name of the map to the northeast corner border of our map, that would be map number 3. And the name of that map is Manzanar. So you can easily see how these maps border our map, and they have this nice numbered list next to it. That is the new technique that they have developed. Okay, now the next question deals with contour lines, contour intervals, and the units of those. So you recall from our lectures on contour lines about maps in general, that a contour line represents a point of equal value in elevation above sea level. The interval at which those contour lines are spaced, as far as their value increments go, is always going to be clearly stated at the bottom of the map here. So it does indeed, we're looking at the Mount Whitney quadrangle here, and at the very bottom of the map, it says contour interval 20 meters. Now notice that this map is in units of meters, it's in metric. But when we look at the SoCal map, and we look at the bottom of the page, I'm going to zoom in so we can look for the contour interval. It says the contour interval is 20 feet. So notice that the units are different on each of the maps. And because here in the United States, we don't use the metric system very often, but we would like all of our geography students to be comfortable converting back and forth between English and metric, it is important that you make note on your handout of how many feet there are in a meter. Now, if you don't happen to know that off the top of your head, the nice thing about the Mount Whitney quad is that they've actually told us here, when we look at the contour interval in meters, it says to convert meters to feet, multiply by 3.2808, which literally means that every 1 meter contains 3.2808 feet. So that's how many feet there are in 1 meter. Now, because the Mount Whitney map is in the contour interval is in units of meters, and it's 20 meters, if we wanted to know what is that contour interval in units of feet, we would just have to multiply our 20 meters by 3.2808 feet per meter to get units of feet. And when you do that, you come up with just under 66 feet. So 65.6 feet is the contour interval of every one of these contour lines on here represents about 66 feet of elevation change. If you're going uphill, it's every single line represents 66 feet of increase, or if you're going downhill, you're descending 66 feet with every one of these contour lines. On the SoCal quad, because this area is flatter, it's not as steep, every contour line going downhill represents only 20 feet of descent, or going uphill, only 20 feet of increase in elevation with every contour line. Now notice, we have talked about this already, that some of the contour lines are a little bit darker than the other contour lines. So right here, when we look at this 200, that is what we call an index contour. So it kind of stands out a little bit more than the normal contour lines. It's still part of the 20-foot contour interval, but the reason the map makers give a little bit more weight to those lines is because if you're trying to count really fast and you're trying to maybe count what's the elevation change, say from here up to this line here, counting every single one in 20s takes a little bit longer than if we could do bigger intervals. So these index contours are also on a regular interval pattern, and we can kind of determine that by looking for two index contour lines, and I'm going to use these two here. This is the 200, and I know I'm going uphill in this direction because I see these sort of circles happening, the top of a peak, and I also see higher numbers. So if I look for that next darker contour line, that next index contour, and I follow that line up to where its value is noted, notice it's 300 feet. So between this index contour interval and this index contour interval, we've gone from 200 feet to 300 feet, and the next one would be 400 feet, and the next one would be 500 feet. So they are going every 100 feet. So the index contour interval on the SoCal quad is 100 feet. Let's see if we can figure out what it is on the Mount Whitney quadrangle. Let's look in the north west area of the map, kind of near Mount Young, but maybe to the west of there. And I see a nice, clear, dark index contour line with a value of 3,400. Now remember, these are in units of meters. And then I see other dark index contour lines that maybe aren't marked with a value. But then I see one up here that has a value of 3,800. So I've gone from 34, and I have 1, 2, 3, and then the fourth one is 3,800. So the map maker is always going to use nice, even increments. So I'm going to guess 100 meter as the index contour interval here. So if I start out at 3,400 and I end up on the fourth line at 3,800, I'm going to guess 100. So if this is 3,400, this next one would be 35, the next one would be 36, the next one would be 3,700, and the next one should be 3,800. And if we follow that line around to where it's marked, it is indeed 3,800, which tells me that the index contour interval of the Mount Whitney quadrangle is 100 meters. Now notice that the spacing between contour lines, each individual contour line, varies quite a bit in the map itself. There are some areas, for example, over here, where contour lines are spaced fairly widely apart from one another. And then there are areas over here, say by Mount Hale, where the contour lines are spaced very, very tightly together. Now, because contour lines indicate change in elevation from one contour line to the next, if we have contour lines spaced widely apart, that means the elevation is there's much more of a gradual change in elevation, and therefore we would say the slope of the landscape, the slope of the terrain, is more gentle or more gradual in this region here. Whereas if we look over to our east towards Mount Hale, where we have contour lines spaced so closely together, every single one of those lines represents, I think we said 66 feet of elevation change over a much shorter distance. this indicates very, very steep topography in the landscape, or a very, very steep slope. So there is indeed that relationship between the spacing of the contour lines, how far apart they are from one another, and what the slope of the landscape is. So that you can kind of zoom out from a map. And let's do that with the Mount Whitney so we can just get sort of that bird's eye view. And if we had to pick the areas with the steepest slope, well, it looks like right all along here, which is that ridge top of the Sierra Nevada mountains, is very, very steep. Some of the flatter areas seem to be down around here, maybe over in this region here. So that's one of the really nice things about contour line spacing, is it tells us a lot about what the slope of the land, what the steepness of the topography is like on the ground. The other thing we want to look at with our contour lines are creeks and streams. And what do contour lines do? How do they behave to indicate what the topography is doing? How do they behave on the map? What is the shape of those contour lines like on the map? So we're going to look for some streams, and I'm going to zoom in here on the Mount Whitney quad. And I'm just going to look at this stream right in here in sort of the southwestern region of the map. Doesn't actually even have a name, this waterway, but I know it's water. It's a blue line. And I know that water always flows downhill. And if we look at some of the values of our index contours, we know this is 3,800 up here. It's going down to 3,400. So I know that water will flow downhill. So this is the downhill direction where the water is actually traveling, down to the lower left portion of the map. So the creek is in the middle here, and we see the contour lines, and you'll notice how the contour lines kind of travel parallel sort of to the creek and then bend, make a sharp bend as they reach the water. And every single one of those contour lines here is doing that same kind of bending pattern. Now, the shape of that bend looks like the letter V. I know it's upside down, but if we were to rotate the map, we would actually say that's the letter V. That's a V shape. And if we look at any other creeks, we will see a similar pattern. So right in here, we see that V shape bending of the contour lines. If we come down here to this creek, we also see that V shape happening. So the V shape, when contour lines make that V shape, that's a really good indication that you're in a stream valley or a creek, okay? Maybe there's no water in it, all year round. But we still know that that topography would be very steep-sided. It would be kind of like going down into a little canyon. Now, the nice thing about the contour lines on the topographic map is that the V, the point of that V, always points upstream or uphill, because water, of course, flows downhill. So the V is pointing in the uphill direction. The opening or the wide part of the V always indicates the direction of downhill. So I'd like you to make a little sketch on your handout of this pattern, this shape, and we do call this the rule of V's. So when we see those V's on a map, it tells us that, yes, indeed, there's a little stream valley or a creek or a canyon, and I know which way is uphill because the V points in the uphill direction, and I know which way is downhill because the wide opening of the V points downhill. One other nice rule that we can use to understand topography based on contour line shape is what we call the rule of O's, like the letter O. And this refers to mountain peaks. So here we have a mountain peak. It's called Mount Guillotte. And although this isn't a perfectly shaped letter O, we do see sort of a circular pattern going on around the center or the top of Mount Guillotte. But that same circular loop continues as we go downhill towards the edges, the base of Mount Guyot. So this rule basically applies to peaks of all kinds. We can look for other peaks. So here's another peak over here. We can continue up the map and look for other peaks. So where we see these O shapes, that smallest circle is indicating the top of the hill. The largest circle on the outside, like maybe down around here, indicates the base of the hill. But we know if we're seeing those circles, we're seeing a hill or a peak. Let's take a look at the Mount Whitney quad, the Soquel quad, and see if we see a similar pattern going on. Let me zoom out a little bit first. And right over here, we have a mount. It's called Monte Toyon. And in fact, we do see these circles. We see two circles. So this is a pattern that you'll see on maps. Wherever we have these hills, the top of the hill, smallest circle, the largest circle on the map, indicating the base of that hill or mountain. So I'd like you to make a couple of sketches on your handout just to indicate that you understand the rules of O's and the rule of V's, and you can identify those features based on what contour lines are doing, whether it's a creek or a stream canyon, or whether it is a hill or a mountaintop. Now we would like to look at determining highest and lowest elevations of places on our map and calculating the total topographic relief for each map. So let's begin with the Soquel quadrangle, and let's find the highest point. Now, a lot of times students say, where do I begin finding the highest point on a map? And there's not one steadfast rule, but there are some indicators that will definitely help us. For example, when we look at the Soquel quadrangle, there's ocean on here. We know that the lowest elevation of land is where it meets the ocean. That's what we generally call sea level. So moving in any direction away from the ocean, we should be going somewhat uphill. Although some areas might be more hilly than other areas. Even if you did not know anything about this area of Santa Cruz County, you could look for things like closely spaced contour lines where there's steep topography, or look for numbers maybe that are high on those index contours. So that's going to require us to zoom in a bit on the map. And we could begin in the northwest region of the map. And when I look at some of those hilly areas, I see probably the highest numbers are 300 up in here. So I'm going to scan over towards the center and even the northeast portions of the map and look for maybe higher values. I see a 400, I see a 500, I see another 500 over here. So I'm going to look now for maybe a mountain peak. So here's a little peak, and here's another peak. Now, using our knowledge of index contours and the rule of O's, if I were to choose this mountain peak and to try and determine if this is the highest one right here, as opposed to Monte Toyon, I know that this contour in this index contour is 500 feet. The next index contour uphill is 600 feet, which happens to be the top of that mountain. That's the smallest circle. If I look over at Monte Toyon to compare, here's my 500-foot index contour. The next index contour up is worth 600. And then there's actually some regular contour lines above that. So I can count now by 20s because that is the index contour interval. So this would be 620. Let me zoom in again so we can really see this up close. So here's 500, 600, 620, 640. And it's the same for this other, they're kind of double or twin peaks here, okay? So 600, 620, 640. Now, you could keep looking on this map and see if you can beat the 640 of Monte Toyon, but you're not gonna find a higher peak than that because I have searched it very hard, and this is the highest peak. So on your handout, your highest elevation is 640, and it's feet because those are the units on the SoCal quadrangle. Now the lowest, if we're looking at land areas only, which is what our handout is asking us for, the lowest is basically where the land meets the water, and that is what we would call zero or sea level. So highest peak, 640 feet, lowest is 0 if we're talking about land areas only. And calculating topographic relief, of course, is the highest elevation minus the lowest elevation, which in this case is 640 feet minus 0 feet, which equals a total relief of 640 feet. But what if we wanted to include the ocean areas on the total relief of this map? Because of course the ocean and the ocean floor is indeed part of this map. So if we want to determine that, the first thing we want to look at are the contour lines on the ocean floor. Now notice that these contour lines are shown in blue, and we cannot assume that the units, the numbers given on these contour lines on the ocean floor are the same units as on land. But on the map, it should tell us. So if you look down at the bottom, it does indeed say something about depth curves. So let me zoom in one more time. Here we go. So here it says depth curves in feet. That means the units of these values on the blue contour lines on the ocean floor are in units of feet. That's important to make sure because sometimes the land areas will be in feet and the ocean will be in meters or vice versa. So we know that the units are feet. So what is the lowest depth contour line that we can find on the map? And it's probably the one farthest offshore. And if you look at these numbers, indeed, it is the one that is farthest offshore. So zooming in again, we can see that it's a value of 180 feet, and that is below sea level. When elevations are below sea level, we always put a negative number in front of them. So in the next question where I'm asking you to include both land areas and ocean areas to calculate the total maximum relief for the entire map, including land and ocean, our highest elevation is still Monte Toyon, which has an elevation of 640 feet. But the lowest elevation now is on the ocean floor with a value of negative 180 feet. So in other words, if you were to travel from Monte Toyon up here in the northeast corner down to the lowest portion on the seafloor for this map, what is the total vertical change, number of feet that you would descend down? So again, we're going to use our formula for topographic relief. So we have our 640 feet highest minus the negative 180 feet on the ocean floor. And remember that a minus a negative in math equals a positive. So we get a total relief of 820 feet. That is interesting how that happens when we have a value below sea level, a negative elevation, we have to add them. Okay, let's do the same for the Mount Whitney quadrangle. So Mount Whitney, the really nice thing about the Mount Whitney quadrangle is that the name of the quadrangle is the name of the highest peak on the map. So right here in pretty much center, we have Mount Whitney. And we have a benchmark there, which is what the BM stands for. So at the very, very top of Mount Whitney, if you climb up to the very top, you're going to see a benchmark in the rock. And it has been ground truthed or surveyed. And it gives us an elevation of 4,416.9, and that is meters. Remember that the Mount Whitney quadrangle is in units of meters, okay? If you wanted to determine the elevation in feet, what do you need to do? Remember that the map maker makes it really easy for us and tells us that to convert meters to feet, we multiply by 3.2808. So if we multiply the elevation of Mount Whitney in meters by 3.2808 feet per meter, we will get the total number, a total elevation of Mount Whitney in units of feet. So make sure that you can do that. The lowest elevation, determining what is the lowest elevation, where is the lowest elevation, is a little bit trickier, but I do give you a clue, and I tell you on the handout to look in the region around Guyot Creek. So that is kind of in the southwest area of the map. Here is Mount Guyot, and here is Guyot Creek. Now, Guyot Creek, of course, we can see the V shapes of the contour line, so we know that the water is flowing downhill in this direction towards the opening of the V's, right, like this. But the actual lowest area happens to be right about here on the edge of the map. Now, you can play around with this and count for yourselves. I'm just going to walk you through how I got this answer. First of all, I'm going to use the numbered index contours to help me. So I see that this index contour up here, which of course continues on over into this region, has an elevation of 3,300 meters. And if I'm going downhill this way, I know I'm going by hundreds because we already determined the index contour interval on a previous question. So therefore, this line has an elevation of 3,200, this line has an elevation of 3,100, and then this next dark index contour has an elevation of 3,000. We could also count by 20s backwards from the 3,100 to also determine that that's 3,000. So if we did that, if this is 3,100 and we have a 20-meter contour interval and we're going downhill, so we're subtracting 20 meters every line, this would be 30-80, 30-60, 30-40, 30-20, 3,000. And that is how I determined the lowest elevation. Now you are welcome to search more if you want to and see if you can find anything lower elevation. Like this one comes pretty close over here, but it's not as low as 3,000. So the lowest elevation on the Mount Whitney quadrangle is right here, and it has an elevation of 3,000 meters. So when you're determining the topographic relief for the Mount Whitney quad, remember you're taking the highest elevation, which is Mount Whitney, and you can do this in both meters and feet. And I actually encourage you to practice this in both units, both meters and in feet. So Mount Whitney, you can do it in meters and subtract from that the elevation down here of 3,000 meters. Now, because these are both above sea level, you're not subtracting a minus, you're just doing a straight subtraction. And you could also convert both of them into feet and then give me the topographic relief in units of feet. Okay, so be comfortable doing it both ways. The last couple questions here for this section deal with datum and legends. So I think I just want to talk about datum. So datum, you'll recall from a previous lecture, just tells us the how these elevations are determined. What are we calling zero in order to tell us that Mount Whitney has an elevation of this many meters? So a datum is established by large surveys that are done periodically, like maybe every few decades, by a very large group of organizations well, we do ours in North America. And the datum will be listed in that lower left corner off the map in all of that fine print there. And notice here we have a North American datum of 1927. So this was a survey that was done in 1927 to determine what are we going to call sea level, what are we going to call zero, and what therefore will all of our elevations be referenced to. But then there was a more recent datum done for this map in 1983. So it's really, the values shift a little bit between the 1927 survey and the 1983 survey. The 1983 would be the most accurate. So the datum simply listed on your handout would be North American datum of 1983. For the SoCal quad, and we have to remember this is an older quadrangle, so some of the methods might be a little bit different. Also, the SoCal quadrangle contains ocean areas, which ocean areas, we may use a different type of datum in accordance with the range in tides, the daily tides over a, say, about approximately 20-year period of time. And we can also use those North American datums. So this map actually has a couple of datums that are used. I'm going to zoom in on the fine print at the bottom of the map for us to take a look for information regarding datums, which would be data. So the datum for the ocean areas is mean sea level, which is basically the average of all of the actually, it says datum is mean lower low water. So that's the average of all the lower of the low tides over a 19.6-year period, which has to do with lunar cycles. And that's what they're calling zero for the depth curves. Okay, that's how the water depths are determined, referenced to the average of the low tides. But the land area elevations have to do with the 1927 North American datum. So you'll notice over here, because this map does contain ocean data and land data, we actually have two different datums that are used. Now let's move on to some more specific questions about each map. And we're going to go through quite a few questions based on the SoCal quadrangle first. Because we are here at Cabrillo College, I would like us to look at some of the elevations specifically to our campus. So we want to approximate the elevation of the main sort of center of campus, which is located by this purple square here at Cabrillo College. And I'm going to have you guys use as the reference point for a contour line the letter C of the word college. Okay, so you see that contour line that's running through the letter C, that line right there? We want to determine what is the elevation of that line. One of the easiest ways to do this is to find a contour line that is marked, our index contour down here at 100, and then because we're actually going uphill in this direction towards the 200 line, we can count up by 20s, which is our contour interval, to determine the elevation of this line right here. So notice that here's 100, the next line uphill is 120. The next line uphill is 140 feet. So if we follow that 140-foot contour line around, what you're going to notice is that is the line that goes through C of the word college at Cabrillo College, lower campus, we would call this. This is where all the sports facilities are, and the track and the swimming pool, etc. Of campus is down in here. The next question asks, what is the elevation of the upper portion of campus, which is, we're going to use this large purple square here. This is the uppermost building that was built at the time of publication of this map. Since this map was produced or revised, photo revised, there have been some more buildings built up in this region here. But for the purposes of this exercise, we're going to use this purple rectangular building here to determine the elevation of the upper campus. So again, we want to use a marked contour line. So we have a 200-foot index contour here. And again, we're going to count up by 20s with each line going uphill. So this would be 220, 240, and the 260 line goes right through that building. So the upper campus has an elevation of 260 feet. So if you were actually to walk from, say, Lower Campus down here across Soquel Drive and to the uppermost building on our current map, how much elevation would you have gained by walking up that hill? So you're going from 140 feet up to 260 feet, which is a gain of 120 feet. So we can just simply do a subtraction of 260 minus 140, and we get 120 feet uphill that you would have to walk. Next thing we're going to do is find the Mount Diablo meridian. So this red dashed line here has to do with our rectangular survey of tier ranges and section numbers that we have already discussed. But this Mount Diablo meridian runs pretty much north-south. It's not exactly the same as a longitude line, but it's very close. And notice that that meridian actually separates our range numbers from west, going in this direction every 6 miles, to our range numbers in the easterly direction. Again, every 6 miles, we would have a new range number in the easterly direction or the westerly direction. So we see that Mount Diablo meridian, and that's going to be very important to some future questions when we're trying to give the rectangular survey descriptions of certain locations. But for right now, I'm wanting you to use a measuring tool. So we're going to go to our analysis measuring tool. And we're going to measure how far you would have to walk if you went from Cabrillo College, which is maybe right about here where you'd be crossing campus, to the location where the Mount Diablo meridian crosses Soquel Drive, which is right about there. You may want to actually move this up a little bit further. And that would be about 1 mile. Now notice that this line isn't exactly on the Soquel Drive. It's pretty close, but it's hard to get a straight line to follow a curved road exactly, but we're pretty close to a 1 mile distance. You could, of course, convert that into feet. You could convert that distance into kilometers as needed on your handout. Okay, the other thing that we want to talk about is the rectangular survey, which we know we have range numbers, we know we have tier numbers, and we also have these red section numbers that are separated by red dashed lines. So that is the cadastral system of the rectangular survey. But notice that areas east of Rodeo Creek do not have section numbers in them. You're not going to see any red numbered 1 mile square sections to the east. And the reason for that is that this area had been surveyed prior to California becoming part of the United States by either Spain or Mexico, both of whom had separate periods of time when they ruled, if you will, California. So because those countries had surveyed some of these lands using their meets and bounds cadastral system, which is the cadastral system that was used prior to the rectangular survey, we do not have any evidence of the rectangular survey here. So these, most of these areas were land grants that were granted to private citizens or maybe to very important people in Spanish government or royalty, and they were given names. So for example, one name here, and they're all in capital letters, is Arroyo del Rodeo. So that would have been one big land grant, probably extending from the creek bed of Rodeo Creek to the creek bed of the Soquel Creek, right in here. Another land grant example is Soquel, which is the original spelling of our current town, city of Soquel. Another one is Aptos. So we also see Aptos listed here in capital letters. as another land grant. Again, we do not have any tier, range, or section numbers in these areas as they were previously surveyed under the meets and bounds cadastral system. So a couple of more things before we move on to the Mount Whitney quad. On the SoCal quad, we want you to be able to determine the location of specific places using the rectangular surveys descriptions, which is tier, range, and section numbers. So first location is Chaminade School, which is in the northwest corner of the map. And notice here a building with a flag on the top. That is the symbol used by the USGS for schools. So although the name of Chaminade School may extend across that section boundary line, the actual school is located right here. So let's begin with our tier number. So remember that the tier numbers are always going to be on the outside of the map, on the edges of the map. And we see here T11S, T11 South. And if we look all the way down and all the way up the map, we don't see any other tier number. And that's because tier numbers extend for 6 miles. So the map location just happens to be all located within the T11 South tier 6-mile range. So T11S is the tier location for Chaminade School. The range number is going to be on the top or the bottom of the edges of the map, again in red lettering. So because we're west of the Mount Diablo meridian, we are in the range 1 west. And again, that extends for 6 miles, so we don't actually see range 2 west yet. That would be off the map. The final description is the section number. So the section numbers, again, are going to be in red. And we can see the dashed boundary line for section 5. We don't actually see all of section 5 in this map view, but Chaminade School is indeed in section 5. The other location for practicing your rectangular survey descriptions of property or locations is Twin Lakes State Beach. So tier number, again, is going to be the same. The range number is also going to be the same, but the section number will be different. So as we look for the red numbers, we see that Twin Lakes Beach is within this red dashed line boundary in section number 20. The last portion of our handout deals with specific questions about the Mount Whitney quad. We're going to begin by measuring the approximate length from north to south of Topographic Lake on the Mount Whitney quad. So in order to measure, we're going to use the measuring tool. And from north to south, I'm going to begin my point at the northernmost end of the lake. And, whoops, I didn't quite get it there. Let me move it up to the northernmost end of the lake and then extend that line down to the south. I want to actually straighten this out a little so we get a straight shot from north to south. And I get a distance of 0.51, slightly lower there, 0.51 miles. So that is the distance in miles, but I'm asking you to give me that distance in feet, which means that you need to convert from miles to feet. And you may recall that every 1 mile contains 5,280 feet. So if you multiply that amount, 5,280 by 0.51 of a mile, that'll give you the number of feet. We can do the same thing for determining the distance from east to west. So let's pick kind of the widest point on the lake's edge on the western boundary and measure across due east. And I'm going to straighten that line out so it's a little more accurate. Oops. Just move it up a little bit. And There we go. I'm getting 0.35 miles. Notice that geospatial distance tool measurement box pops up. So 0.35 miles, again, we're going to multiply that by 5,280 to get the width in feet of the lake. Next question has to do with Mount Russell. So I'm going to turn off the measuring tool and search for Mount Russell. And sometimes you just have to search a little bit before you find places. Here's Mount Russell. Let me zoom in so we can see Mount Russell a little more clearly. There it is, Mount Russell. So if you were at Mount Russell, the question is, what is the general direction you would be traveling to get to this lake? Obviously, it's not north, but it's not due east either. It's somewhere between the two. So we would say in a northeasterly direction to go from Mount Russell to that lake. The next question asks about a lake called Sky Blue Lake. So first thing we want to do is find Sky Blue Lake. And here it is. We're asked, what is the water level? So what is the elevation at the level of the water? And so here on our USGS maps, and you'll notice on many of these lakes, some lakes that don't even have names, we do have water levels. So WL stands for water level, and that would be 3,519 meters. The next question has to do with Consultation Lake and Wotan's Throne. So let's find those places. Here's Consultation Lake, and here is Wotan's Throne. Let me zoom in even further on this area. Okay, so how many meters of elevation would you ascend, meaning would you go up, if you started out at Consultation Lake, and we're going to use the water level of the lake, which is 3,560 meters, to the top of Wotan's Throne. Now, Wotan's Throne at the top doesn't have a benchmark with an elevation there, and we don't have any contour lines that are marked very clearly close by. But what we can do is we can use these benchmarks over here to determine the elevation of this index contour. So you see this dark index contour here? It's very, very close to this benchmark of 3,600 meters. And it's also very close to this benchmark of 3,614 meters. So this index contour line, we can assume, based on those benchmark values, has an elevation of 3,600 meters. Then, if we're going to Wotan's Throne, we're actually going uphill towards the rule of O's, tells us we're going in an uphill direction. So this contour, index contour, would have a value of 3,700 meters. This would have 3,800 meters. And then we have to count by 20s. So 3,820, 3,840, 3,860, and 3,880. So the top of Wotan's Throne is 3,880 meters. The water level at Consultation Lake is 3,560 meters. So if you were walking uphill from the lake shore up to the top of Wotan's Throne, you can do the math on that and determine how many meters of elevation you would climb. I'd also like you to convert that into feet, just to practice the conversions between metric and English units. Now let's look at some specific places and determine their descriptions using the rectangular survey. So let's start with Wotan's Throne, since we're here at Wotan's Throne. And you'll probably immediately say, oh, that's in section number 4, because we can see that red number, we can see the dashed red lines outlining that 1 mile square section. But we need to come to the edges of the map to determine the tier and range numbers. So here, this red dashed line, it's a little bit of a heavier line. It's important because it happens to be the boundary between two different tier numbers on our map. So tier 15 south is above that thick red dashed line, and tier 16 south is below. So Wotan's Throne, this section number, is actually in tier 16 south. And then the range number, we have to go either to the top or the bottom of the page to find the range number. And we see here 34 east. And we don't see any other range number listed. So we can make the assumption that this entire map is in the range of 34 east. So we have the description for where Wotan's Throne is. Now let's look for Iceberg Lake and Mirror Lake and see if we can figure out their location. So here's Iceberg Lake. Iceberg Lake we see is in section 33. The tier number happens to be in the tier above that dark red boundary line, so that's 15 south, but the range number is going to be the same for the whole map. The third lake, Mirror Lake, take a look. The Mirror Lake, there it is, right there. Okay, Mirror Lake, small lake, it's in section 3 of tier 16 south, and again, range 34 east. Now, notice that this boundary line right here, which is basically the crest of the Sierra Nevada, to the west of there are no section numbers. So we have section numbers all in here, but we have no section numbers to the west. Why would that be? So we have to think back to our discussion of cadastral systems and what areas or what kinds of lands are not included in the rectangular survey. And you may recall that national parks are not included in the rectangular survey. And sure enough, all of this area here to the west side of the crest of the Sierra Nevada is part of Sequoia National Park. Therefore, these lands will not be owned for private purposes, private ownership, as they are a public resource, a national resource, and therefore we do not impose the rectangular survey on those public lands. Okay, let's look at a couple of places, Mount Chamberlain and Mount Pickering. So let's first find them. Mount Chamberlain and Mount Pickering. Here's Mount Pickering and here's Mount Chamberlain. Okay, let me center them on the screen. So if you hiked southeastward from Mount Chamberlain to Mount Pickering, so you'd be kind of heading southeastward, would you be walking uphill or downhill or some kind of combination of up and down? I want you to describe the slope, what the slope would be like from start to finish if you started here and you ended here. So we only actually have one index contour line marked, this 3,800 line right here. So we know it's 3,800 meters over here. It's also 3,800 meters over here. So we're going uphill here from Mount Chamberlain. So Mount Chamberlain is, there's 3,800, 3,900, 4,000 meters. Mount Chamberlain, the top of Mount Chamberlain is 4,000 meters. So if we were walking towards Mount Pickering this way, we would initially go downhill, right? We might even stop for lunch at this pretty little lake here. And then after the lake, we would start going uphill again, because notice here's the 3,800 and we're going to go uphill towards Mount Pickering. So we would initially go downhill and then we would climb uphill to Mount Pickering. If we didn't want to have to do too much down and up, we could probably go down to this contour of 3,800 and take the long flat route around and then go uphill to Mount Pickering. Mount Pickering, is Mount Pickering the same elevation, higher or lower than Mount Chamberlain? Well, let's see if we can figure that out. If this is 3,800 meters, this is 3,900, this is 4,000, and this is 4,100 meters. So actually, Mount Pickering is 100 meters higher in elevation than Mount Chamberlain. So although you go downhill and uphill, ultimately, from your starting point to your ending point, you've gained 100 meters of elevation. The last thing I want us to look at on this map are glaciers. We don't have a whole lot of glaciers left in California. We have some small glaciers, and indeed they are up in our highest mountain ranges, the Sierra Nevada, for example. So here we are in the Sierra Nevada, and I first want to point out how we can identify a glacier from our maps. So glaciers do follow the contour line, so the snow and ice accumulates on a slope, and it too has slope to it. So the map maker actually turns the contour lines blue, and we define the boundaries of a glacier using sort of this dashed blue line to show the extent of that glacial ice. So wherever you see this kind of blue contoured with the blue dashed line perimeter around it, that indicates a glacier. So your last task for this handout is to count the glaciers, okay? And there are quite a lot of them. I mean, just up in here, we're seeing 4 or more glaciers. I'd like you to count them all. And then I'd like you to look at what direction, for the most part, the glaciers are facing. Now, when I say facing, do they face on a south slope? Are they facing south? Are they facing north? Are they facing west or east or something in between? So let's just start with this glacier right here. The red boundary line is the top, basically the crest of the Sierra Nevada. So it slopes downward to the east, or northeast in this case, and it also slopes downward to the west, because this is the very top of the mountain. So this glacier is sitting on a slope that is facing towards this general direction, which is northeast, right? The glacier is not on this side. If it was on this side of the crest, it would be facing south or southwest, but it's not. It's on the northeast facing slope of the Sierra Nevada. When we look at a lot of these other glaciers, we're going to see a very similar pattern. This one is facing more northward. This is on a northeastward. This is on a northward. This is on a more of an eastward. This is due north. So I want you to kind of go through and see if you notice any pattern to the direction that the glaciers are facing. And hopefully you will see a pattern and be able to explain why the majority of the glaciers are facing in a similar direction or directions. Okay, you are finished with the handout. Thank you.